Hello, and welcome. This is your final video for your final exam for the spring semester of Algebra 3-4. Technically, I guess we're in Algebra 4. This is the last video I'm going to have for you guys, and I'm going to cover problems out of the multiple choice packet. I have 20 problems here, based on your requests. Most I'm really going to do, for the most part, is just answer the questions themselves. If I go any farther than that, then it really would be teaching you the concepts again, which I'm trying to avoid doing, because first period class has already taken their final, and that would be unfair for them, etc. However, you always get this opportunity because I am allowed to answer questions out of the packet as long as they're directly involved in that. So I'm going to go straight through these problems. They will be in this order. Also with me are my calculator and the answer key to make sure that I'm not screwing anything up, at least when I look at the answer and say, oh, look, this is what it is. So I'm going to jump straight into it, but before that, I will just make sure that I cover a few things here really quickly for y'all. Some things that are, yes, they are true, and things that are actually not so true within the same category. So the first thing here is on logs. If you take log base b of a, if you want to use the calculator, that is log of a over log of b. Okay, now there is a property, if you take the log of a fraction, you get to subtract two different logs with those values, log of a minus log of b. Sometimes people take this property and they decide to turn it into this property right here, meaning like the same thing. The only difference is, look, log of a over b and log of a over log of b, they're not the same thing. And there may be some sense that's made into that. Why can you just take 6 divided by 2 and make that the same as 6 minus 2? No, you can't do that. This is the function. This log is a function of something. You calculate something, and these happen to be the same thing. Remember, logs are exponents, and they work in those tricky ways. So there's that. Now, log of a over log of b is log base b of a. Okay. Next one, which I've talked about in considerable length, a times b over b is indeed b, or a times b over a is indeed b. I can cross out the a's on top and bottom because they are common multiples on top and bottom. You're multiplying b times a, and then you're dividing by a. So once you divide what you multiplied, then yeah, those cancel each other out. What don't cancel out is if you add a to b, and then you divide by a. Adding something and then dividing it out is not the same thing as getting back to your number. Subtracting it out would be a plus b minus a equals b, but a plus b over a doesn't equal b. So you can't just cancel out these guys right here and say that's okay. Of course that's not okay. So I should just, like while I'm here, I should go, In order to do it on top and bottom, you need common multiples. Third one, you know your formulas like the ellipse equation, and when you're creating an ellipse equation, your a value will always be greater than your b value. I guess the main reason is because a represents your major axis, and as you know, a major axis compared to that of a minor axis is bigger. It's greater in length. Hyperbolas, a will always refer to your transverse axis, and your transverse axis does not have to be bigger than your conjugate axis. Hyperbolas, a is not always necessarily greater than b, so you cannot say that this is true. They don't have to be. It only has to be the positive value. This is something I didn't think I'd have to bring up, but then I saw your tests, your most recent ones. People went for the extra credit, and they were taking the square root of a sum, and they were canceling out their squares, and that's just so not true. So let's go back over here. You can split apart the square root of a product to the product of two square roots. You can distribute a square into a product and make it the product of two squares. You cannot, however, split apart the square root of a sum and make it the sum of two square roots. That is not true, and you cannot distribute a square into a sum and make it the sum of two squares. You definitely know the bottom one. You know that one is a squared plus 2ab plus b squared. People lucked out on their problem because their x value was 0 and the extra credit and all this stuff. But no, that's not necessarily a true statement. I wouldn't bank on that in a test. So truths and untruths, the untruths are right there. Those are not true. These are indeed. Okay, I'm going to start doing some problems. Away we go. I'm starting off with number 2, as I said I would. Write the expression as a single logarithm. Now, when you're doing this, obviously, as they're saying, make it a single logarithm, and you're going to condense. So I'm going to work some properties into here. I'm going to take these values, this 5 and this 2 here, and I'm going to put them in the exponents of their respective logs. this will make this log base b of q to the 5th power plus log base b of y squared. Now to write it as a single log after that, because they both share the same base, I can now condense these so that they are log base b of q to the 5th times y squared. And that is what happens when you condense it. That one looks like A, unless I see something incorrect there. Looks good. Looks A, and if I look at my answer sheet, yep, A is correct, and there it is. We get A. So this is where I said this actually might go pretty quickly, because maybe I do a few of these problems and they go faster than... If you think about it, if a video is an hour long, and if I'm doing 20 problems, it takes 3 minutes per problem. That took a little more than a minute, so I think we're in pretty good shape. Number 3, another log problem here. I'm going to do the same thing. This is about condensing this into a single log. So I'm going to take that 4 and put it in with the x. I'm going to take... You can do this 2 different ways, and I'll show you both different ways to do it. You know, I'll stretch out time a couple ways. First, I'm going to take the 6 and put it in with the stuff, but I'm going to put it on the outside over there. So this will be log of x to the 4th minus log of x plus 2 to the 6th power. Notice, I really like the parentheses around logs as well as the ones around the function there. Because it's subtraction, these will be divided here. So this will become log of x to the 4th over x plus 2 to the 6th power. That would be your final answer. That exists... Oh, it doesn't exist anywhere, so it must be D, none of these. And I look at my answer sheet, yes, that's true. It does end up being D. How was I talking about a different way? Well, let's say that we look at that problem again. I'll go ahead and rewrite it. Okay, what if, when I take that 4 up into the x, what if instead I take a negative 6 up into there? So when I rewrite this here, it's going to end up looking like log of x to the 4th. Now, this is plus negative 6, right? So if I brought up a negative 6, this would be plus log of x plus 2 to the negative 6th power. And as you know, a negative 6th power is 1 over x plus 2 to the positive 6th power. So this would be log of x to the 4th plus log of 1 over x plus 2 to the 6th power. And look what happens, because it's a plus, now we're going to multiply. So when you multiply these two together, this would be log of x plus 4 times that. And so it goes on top, and notice how it just ends up becoming the same thing as it was before. And as you could see, it was not any of these other answers, and you can, I guess, see what the other ones are. And, well, those aren't that answers. So your final answer there is D. Okay, looks like we're jumping ahead to number 6 here. We got to solve for A. Yeah, solve for A. So there are a couple ways. Once again, if there's something I can do with this video, I'll show you the couple ways you can do every single problem. I take a look at this problem, and one way I can go about this problem is go like, well, if I rewrite the equation, I can say this is A over factoring, A plus 6 times A minus 6, plus 2 over A minus 6 equals 1 over A plus 6. And what I could do is I could seek a common denominator for everything. So this thing has multiples of A plus 6 and A minus 6. This term, this specific term here, is missing an A plus 6 on top and bottom. If I multiplied that there, if I multiplied this by A minus 6 over A minus 6, then as you can see, what we seem to have here is a little common denominator. So that becomes A over A plus 6 times A minus 6 plus, now this is a this is 2A plus 12. If I distribute that on bottom, I'll just keep it as A plus 6 times A minus 6 equals A minus 6 over A plus 6 times A minus 6. Okay, so from here, I could really decide to do this one of 2 ways. Either way is not going to... Well, I guess one way wouldn't be as good as the other way. Really. So maybe I will just do this one way. I have the same thing on the bottom everywhere. Okay. Now, I've had a habit of telling you guys, if you have the same thing on the bottom everywhere, then you can cross them out. Now, I did explain why, but I did not give the math behind it as much as I should have, because I think what needs to happen here is you guys really need to say, they don't just cross out what math happens, because sometimes you cross them out in inopportune times, such as when this is not an equation, when it's an expression. Okay, you can't just cross things out in an expression. You're crossing out part of your value. But here, if you multiply both sides by the same value, by the least common multiple, so to speak, now they do go away. A plus 6 times a minus 6, all divided by this in each term, they will cancel out with this. So, no, I didn't have to distribute this into here, but that is what cancels them out, multiplying both sides by a plus 6 times a minus 6. The only other thing that I was going to say about a different way you can do this problem is if I combine these as one term on this side, and then I cross multiply. But you might see why that's troublesome, because you'd have cubic terms, and I don't really want to dig into that. Anyway, if this plus this equals, if this over that plus this over that equals this over that, then this plus this equals this. So a plus 2a plus 12 equals a minus 6, and we can solve for a. We get 3a plus 12 equals a minus 6. 2a equals negative 18, and a equals negative 9. Now, there is a possibility that if you did do this in a certain different fashion, maybe you multiply by some certain numbers and you actually, how do I say it? You get quadratics and you solve, because you can see where there's like a negative 6 and a 6 here. It's possible that you could have solved it in a different way and you could have gotten those numbers along with negative 9. You have to check for extraneous solutions. So this negative 9 here that I got, I want to substitute back into my original equation and see if there's any chance that I can be dividing by 0. In this case, it looks like no, I won't be dividing by 0 anywhere. If I had negative 6 or 6 as my answer, yeah, I'd be dividing by 0 in some cases, and negative 6 or 6 would have been an extraneous solution. So negative 9a seems to be your final answer. Oops, excuse me. And checking my answer book. Yep. So it's A. Number 10, graph the logarithmic equation. Okay, if there are ways that you're going to graph this, one way you could always do is a table. So if you'd like to graph using a table, go ahead, knock yourself out, plug in values for x and y, and figure out what you get. However, if we use kind of a form that we've been looking at here, log base b of x minus h plus k, we could have a stretch factor, but we haven't looked at any with a stretch factor other than maybe making it negative. But if we have this form here, I'm going to make use of every one of these values. Now, hk isn't a center or a vertex, but it is a value that I'm going to start from in a way. Not as a hk, but using these numbers. First, what I'm going to do is keep in mind some properties of logs that I know. For instance, the log of 0 is undefined, or is a domain error. You can't take the log of 0. Domain error, and that word domain really means something. And the log of 1 is 0. So I'm going to use those two numbers to my advantage. First one is taking the log of 0. If I have a certain value for x, like let's say the equation looks like this, which I do believe this is not true. But if I saw the equation looking like this, the x value that makes my log become 0 is 0. If x equals 0, I have domain error. You can't take the log of 0 or negative numbers. You can take the log of anything greater than 0, but at 0, I'm getting a restriction. So at x equals 0, that would appear as your asymptote. I'll go ahead, I'll start, I think it would end up being, this graph right here. I'd create that as my asymptote right there. This is the one that it approaches, and technically, even though the graph kind of shows it like that, it technically never crosses. It keeps approaching it. Because anything greater than it, you start to get some numbers, even negative numbers. Okay. Now, if I take the log of 1, which is always going to be 1 away from your asymptote, if I take the log of 1, then this guy right here will become 0, right? The log of 1 is 0, and 0 minus 3 is negative 3. So the x value, excuse me, the y value that I get when I substitute in this case 1 for x, if x equals 1, my y value becomes negative 3. Basically, whatever value is 1 away from my asymptote, give me 1, and I take the log of 1, I get 0. All that's left is that point right there. So when x is 1, y becomes negative 3. So you can kind of see that that point is obviously not really on here. I guess that would be your point there. And that starts to have the issue of this exact problem, besides what I was talking about. So I am going to redo this problem. But the issue with this problem, really, that I noticed, is that this problem is lacking parentheses. So as I kind of redo the problem, and I know that kind of seemed like a waste of time for you, but I wanted to explain it in one case, and now we're going to explain it in the true case, because this problem was brought to my attention earlier. The answer to this one in your packet is B. Now B is this one right here. And you might be looking at this going, but Mr. Robinson, the stuff that you explained doesn't really apply to this problem, because as you can see, if I'm getting a domain of x equals 0, my asymptote's right here. That's not what this one has. This one has an asymptote of 3. I agree. That's why my beef with this problem is that it is lacking parentheses, and this is why we really need parentheses. The parentheses aren't supposed to be around x. They're supposed to be around x minus 3. This problem really looks like this, and that's the issue with this particular thing. They should have had parentheses around here to specify that. Because they don't have them, it really makes it an issue. And I guarantee there's no issue like that on your final. But the problem does look like this. Which means what x value? If x minus 3 was equal to 0, the x value that gives you 0 in the log is 3. So when x equals 3, you're taking the log of 0, and you can't take the log of 0. Which is why at x equals 3, there is your asymptote that goes right here. And I'm just matching it along with b. Okay. The next point that I'm looking for is when I'm 1 away from the asymptote. Oh, you know what? It would have been this one here, by the way. I guess this would have been your graph at 1, negative 3, now that I think about it. I was looking at this at 2. So this would have been the graph for this problem. And B is the graph for this problem. Because the answer key says B, I'm saying this is what the parentheses are. I'll look at both of them now that I know that this graph isn't wrong. Well, let's go back down. The next point I'm going to do is when I go 1 away from the asymptote. When I'm 1 away from the asymptote, that's when I'm taking the log of 1. Notice this. If x equals 3 right here, 1 away is when x equals 4. You substitute 4 for x, you're going to get 4 minus 3, which is 1. The log of 1 is 0. Log base 2 of 1 is 0. So when x equals 4, y equals 0. When I'm 1 away from my asymptote, I'm getting 0 for y, which is right there. The other points you're going to pick. It doesn't matter if I'm on this graph or on the graph above it. All the points I'm going to pick is now based on this 2 right here, this 2 value. And this 2, much like the exponential graphs, is I'm going to double my distance away from my asymptote every time I increase my values by 1. So when I increase my y values by 1, when I go up 1, I'm going to keep doubling my distance away from the asymptote. Take a look at C. I'm at the point 1, negative 3. When I go up 1 right here, if I'm 1 away right here, now I'm going to be 2 away. I'm going to double my distance away from the asymptote. When I go up another 1, I'm going to be at 4. I'm going to double my distance once again away from my asymptote. When I go up 1 again, I'm going to be 8 away. I'm doubling the distance like 4. And this keeps doubling. If I go down 1, I will halve my distance away. Like that. If I go down 1, I will halve my distance away. And that's what your graph looks like on C. On B, on your quote-unquote correct answer, when I go up 1, I'm going to double my distance away from my asymptote. Before I was 1 away, now I'm 2 away. When I go up another 1, I'll be quadruple. I'll double my distance from 2. I'll be, well, that's not right. Let's see. When I go up 1, let's line that height up. I'll be about right there. Yeah, that's right. Is that right? No, the other one was right. It was right here. Because this is 1, 2, 3, 4 away. When I go up another 1, I will double that distance once again. I guess I'm like up here. So this is 1 away, 2 away, 4 away, 8 away. Same with this. When I go down 1, I'm going to have my distance away and such. So that's what that graph looks like. Maybe we'll run into another log graph, but maybe not. And if so, you can always take a look at my old log videos. But that answer is B, although that's iffy. If it was y equals log base 2 of x minus 3 like that, your answer would be C. But because the parentheses are wrapped around here, it's B. And I'm only doing that because the answer in the booklet says that. Well, here's another log problem. And look at this. They do use parentheses this time. Alright, so I guess I get to re-explain it one more time. Now, one thing I'm going to put in here is this is of base 10. But you know what? It's good you get to see another one. Okay, here's another log graph. Once again, first thing I'm going to do is find the asymptote. And that's when I'm taking the log of 0. When x is negative 1, that's where my asymptote's going to be. So I'm going to go and graph this one on the side first, and then I'm going to match it with one of my graphs. That way you can kind of trust that we're doing it correctly after you match it, after you match what you've done. So let's go ahead and do that. Now this won't look perfect by any stretch. Looks like I have to go down to -7 at some point, so I'm just going to go ahead and do that. Okay, so first thing I'm going to do is go on ahead with my asymptote, like I was talking about, at x equals -1. Because I substitute -1 for x, I'm going to be taking the log of 0, which is something you can't do. And there's my domain stoppage right there. Everything's going to start going to the right thereafter. The one that's 1 over, when I get x equals 0, when x equals 0, I'm going to be taking the log of 1. Notice that. Every time I go 1 over for my asymptote, I'll be taking the log of 1. Log of 1 is 0, so this kind of goes away. And what does y equal when x equals 0 when I'm 1 over? Y equals -7. So there's another point on my graph that is at 1, -7. Or that's at 0, -7. That's not very bright. Let's do red. Okay, every point after that will be when I go up 1, I'm going to take this number and multiply that distance away from my asymptote. When I go up 1, I'm going to multiply my distance away from my asymptote by 10. So obviously you can tell this already starts to shoot very far away like that. If I went up another 1, I'd be multiplying this distance away by another multiple of 10, which is 100. I'd be 100 away. I'd be way off the screen. So you can see why these things are shooting out like that. But what about going the other way? If I want 1 down, I'd divide this distance by 10. I'd be 1/10 away from the asymptote. So you can see how this goes very quickly from here and shooting downward. Not a pretty graph, but notice how it does that, right? I'm guessing all your graphs here are going to do that. So which one matches with that? Well, it's the first one. This first one right here is at 0, -7 right there. At x equals -1 is your asymptote. And you can see how the other ones do not match. This one, I guess, would have been the next closest, but that's at 0. It's +7. That's not where that value is. And you can check those out. But your answer here is A. Let's make sure. Yep, it is. In terms of multiple choice stuff, the way that you can recognize what this problem is without doing any work at all is visualize some of the work. Say, I'm going to have to multiply these by -5 to some powers. Like -5 the first time is going to be raised to the 0 power. And that's an even number, or that's a positive number for an even power. Next time I'm going to raise -5 to the first power, and that's a negative number because it's to an odd power. So that would end up alternating your signs. So I already know that A and C are out because my signs will have to alternate when I do this. Next thing I know is that I am raising I am doing powers of -5 in a way, so I will be raising these to certain powers, which means my numbers are going to keep going up, up, and up. These ones in A and B specifically, are just the numbers in Pascal's triangle. I'll write out Pascal's triangle. I won't explain how to do it for the sake of whatever. But I'm going to write some of it out all the way to the 6th level. This is level 0, 1, 2, 3, 4, 5, and 6. Okay, now notice how it is symmetrical. Now these numbers do appear on B, but it's not immediately just B. I'm going to expand this binomial, and I'm not going to do the whole thing. For one, I did in class. For 2, there are time constraints. And for 3, I do think you'll know what to be able to do with the rest, especially because you know what the answer is. So I want you to practice some of it here. My very first term, I'm going to take 6, choose 0. That number is 1. Take 6, choose 0. Multiply it by my first term, raised to the 6th power. And then multiply it by my second term, raised to the 0 power. That number ends up being 1 times d to the 6th times 1, which is d to the 6th. As you can see, all of them start off d to the 6th. My next term, I'm going to add 6, choose 1. That's 6. I'm going to multiply that with d to the 5th. That exponent will go down 1. And then I'm going to multiply it by negative 5 to the 1st power. Notice the exponents will always add up to 6. Whatever this number is, 6 plus 0 is 6. 5 plus 1 is 6. And notice how these will keep descending. This will be plus negative 5 to the first is negative 5. 6 times negative 5 is negative 30. So automatically, even if you start to do some of the problem, you'll go, oh, multiple choice problem. Oh, look, I already know which one it is. It's got to be D. I'll do one more with you. Plus, this is 6, choose 2, 15, times d to the 4th power times negative 5 squared. Negative 5 squared is 25. 25 times 15, you guessed it, is 375. Positive 375. You have d to the 4th. So this would keep going. Notice how I'm using Pascal's triangle to help me out. Obviously, like I said, this is also 6, choose 0, 6, choose 1, and 6, choose 2. And these keep going that way. 6, choose 2 is the same as 6, choose 4. 6, choose 1 is the same as 6, choose... Whoops. 6, choose 1 is the same as 6, choose 5. 6, choose 0 is the same as 6, choose 6. And 6, choose 3 is in the middle. So these do have symmetry. However, these did not, because these get bigger because the powers of 5 grow. So your final answer is D. Okay, number 18, let's solve for this log guy here. Well, let's solve for x. Okay. I'm going to look at this two different ways for you. First of all, we have to know this is base 10. Okay. So, first way I'm going to do this is rewrite it. And I'm going to go back to an old school property with exponents. I'm going to go ahead and raise these to powers or with a base of 10 as so. Now, this does not immediately change this, by the way. I'm going to write this in red just so you know it's not true. This does not become x plus 9 minus x. This doesn't just cancel this out immediately. Because when you have exponents subtracted with a certain base, if you remember, you get to keep the base. I mean, in order to keep the base and subtract exponents, your thing on this over here was originally 10 to the first one, divided by 10 to the other one, log 10 of x. And that's 1,000 on this side. Now 10 to the log base 10 of x plus 9 is x plus 9. And now 10 to the log base 10 of x is x. But notice how it's division. See, it's not multiplication. Or it's not subtraction. Even though it looked like subtraction. So remember how we were just talking about that kind of stuff. Subtraction doesn't just turn into division and whatever. Or, you know what I meant. There are special things with exponents that you really have to be careful with. That's one way to get to this step. I can get to the step another way, probably the way that most people would do it. They'd take this initial equation, and they'd condense these logs into one log first, instead of these exponents as separate logs. So I can condense this into log base 10 of x plus 9 over x. So as you can see, we still get right back to what we were talking about. Now, right here, I can do those 10s on both sides. Now, because it's just one log, you can cancel out. That becomes x plus 9 over x equals 1,000. So we're back to the same place as we were down here. Two different ways to do it. Doesn't matter which. You're still doing the same stuff. Okay, we've got to solve for x. I won't go so much guess and check, although I'm sure you could probably run into an answer somehow. But, as you can tell, there are only these options. And you can always, this is multiple choice. You could just try and plug them in and see. But if this had a none of these answer, you'd have to solve for it. Multiply both sides by x. We'll get x plus 9 equals 1000x. Subtract x on both sides. We'll get 9 equals 999x. Divide both sides by 99. You'd get x equals 9 over 999. Or 1 over 111. Now what's the decimal? That's what your calculator's for. However, you could probably look at these and know your answer. 0.3 is about 30%. If you get 1 out of 111 on a test, did you get about 30%? Nah. Did you get 300%? Nah. 10,000%? 11,000%? Nah. You got this one right here. In your calculator, you'll probably get about that number. Your answer is A. 18? Yep, your answer is A. So that's about 0.0090 or something like that. What was it? Yeah, 0.0090. Small number, less than 1%. Okay, write the explicit, for number 24, write the explicit formula for the sequence, then find the fifth term in the sequence. Okay, so one thing that you need to know about this explicit formula is that it's a geometric sequence. The only reason I know that is because they give us an R value. And an R value represents common ratio. Now all of these things, all the geometric sequences really are in this form, y equals a times b to the x powered. That x might have some other stuff, but it's all about growth rate, right? Common ratio is how many times you multiply some number by something, and this is your starting value. So although we look at the equation a little bit differently, our equation looks a little bit more like different letters like this. Now the difference here with the n minus 1 is because it depends on how many terms we're doing. On the first term, we want it to be r to the 0 power to make it 1, so a sub 1 times 1 is a sub 1. We want our first term to be a sub 1. So my a sub 1 is 3. My r is negative 3. It's just going to look like that. That's what that term is. So if you're already looking at your answers, it looks like the only available one really is A. It looks like A is already going to be your answer. But if you want to keep solving, say, how do you get 243? Let's go ahead and take a look. Find the fifth term in the sequence. All right, so I'll get a sub 5 equals 3 times negative 3 to the 5 minus 1 power. So really what you're doing is you're starting, if you think about this sequence, the first number is 3, then you multiply it by negative 3. You get negative 9. You multiply by negative 3 again, you get positive 27. Multiply again, negative 81. And one more time, you get positive 243. There is that fifth answer, but how does the equation make sense of it? Well, you take your first term and you multiply by negative 3 4 times. 1, 2, 3, 4. And that's where that comes from. That's what the equation says. So your final answer is A, it's positive 243. Number 25, write the expression as a single natural logarithm. So just as we did before with the other log problems, the same thing, only this one has a lot more to work with. Notice how this has another negative here, so you can deal with the negative like I did last time if you bring the whole negative up on top. I'm not. I'm just going to take a positive 1/2 up there. So I'm going to take the positive 3 up here, do that with the natural log of A. And take the positive 1/2 and bring that all outside here, all the way on the outside. You know what? In fact, you know what? I'm not going to do that yet. I am going to distribute that negative 1/2 now that I see this problem, because those are parentheses. And I want to take advantage of that. You'll see what I'm talking about. But I'll bring the 3 up. That's natural log of a cubed. I'll go ahead and do minus, and I'll separate them. Minus 1/2 times the natural log of b, minus 1/2 times the natural log of c squared. Notice how in order to condense, sometimes you have to expand. Kind of weird, but true. Because I didn't expand natural logs, I just expanded the 1/2 into there. This was a little bit of condensing, actually. And this was a little bit of expanding here. So I'm going to condense the rest of the way. So bring this 1/2 in there, bring this 1/2 in there, and I'm going to get natural log of a cubed once again, minus, and I'll get natural log of b to the 1/2 power, minus natural log of c squared to the 1/2 power. Okay, I'll do the whole next step in one. I'll do one at a time. First one, natural log of a cubed, minus natural log of b to the 1/2 power is the square root of b. C squared to the 1/2 power, 2 times 1/2 is 1, so this is just natural log of c. So as I write my final equation, this is going to become the natural log of a cubed all over. Now, if these are both subtracted, they'll both be divided, like they'll both be in the denominator. They're being multiplied together in the denominator. Notice I could have factored a negative out and left the plus in, just like it originally was. So you see this as multiplication, but in the denominator. So c gets multiplied in the denominator, so does the square root of b. And that must be one of our answers there. Natural log of a cubed over c root b. Aha! There it is. Final answer in 25 is D. Number 26, write an equation for a graph that is the set of all points. Ooh, like locus, right? Locus of points. In the plane that are equidistant from the point F and the line x equals -6. So before you even have multiple choice, maybe you already identify that this specific graph, this conic, is a parabola. Because it's the only conic that we've looked at with one focus, and making use of this line here. And this is definition of a parabola. It's the locus of points that are equidistant from a point that's called the focus, and line is called the directrix. Whenever I do these, it always helps me to graph them, like in a kind of a cheesy way. But there's F at 6, 0. Here's your directrix. X equals -6. Now the vertex lies immediately in between. That's just one of your points, along with all the other points in it, and all of them would start to curve out in such a way where your focus stays inside your parabola. Like this one, like that. Those would be equidistant. Obviously I didn't draw this very well. But I know that my equation is going to be an x equals positive y squared equation. X equals ay squared, where a is greater than 0. So I know it's not going to be B or D if I did this in a multiple choice approach, if I was doing process of elimination. The rest is figuring out what your stretch factor is, and that's based on the relationship with A and C. This distance here is C, and that's 6, distance from vertex to focus. So if C is 6 and A is 1 over 4C, that's 1 over 24. So your equation is then x equals 1 over 24 y squared. And your vertex is at the origin, which is why there's no shift. So your final answer ends up being A, as the packet also agrees. Okay, number 27, here's an exponential equation. I'm not sure if we have more than this. We'll check and see. But this is the same idea as when I was talking about the log equations. You have a certain form that we look at. And you know how like we couldn't take the log of 0? Remember what logs are? When you take the log of something, your answer is an exponent. You found the exponent to make that happen. So another way of saying that, if you can't take the log of 0, that also means you can't take this to any power and make it 0. Right? There's no x value that you can do to make this 0 unless b itself was 0, but b has to be a value that is not 0 or 1. Otherwise, this wouldn't be an exponential equation. That being said, our number here is 2. You can't raise 2 to any x power to make it 0. Therefore, you cannot get 0 as a value right here at all. So y couldn't ever equal 0. Notice that your k value in this case is plus 0. So your asymptote better be at y equals 0. So I'm going to go ahead and make another makeshift graph here, just like we did last time, and then I'll match up the proper answer with it. That's too dark. I'll make the graph that color. But your graph has an asymptote at y equals 0. Notice as x gets infinitely small, like -1 billion, this becomes a very small number, very close to 0, but never quite becomes it. Okay. The rest of your graph here is I'm going to choose a value for x, at least the way I do it. I'm going to choose a value for x so that I'm going to take 2 to the 0 power, so I get 1. That way I can make use of this 4 here. When x becomes 0, when x is 0, 2 to the 0 power is 1, 4 times 1 is 4, y becomes 4. And that happens all the time. Whenever you raise something to the 0 power, it becomes 1. So I want to make use of this number by making x the value that makes my exponent 0. In this case, it is 0. So when x is 0, y is 1, 2, 3, 4. So there's a point here, 0, 4. From there, I'm going to use this b value of 2, and every single time I go over 1 in the x direction, I'm going to double my distance away from the asymptote. So the first time I go over 1, I'll be going up 8, because that's double the amount of 4. If I went over another one, I'd be going up 16, which is probably somewhere up here. And it keeps increasing. Next one would be up 32. That's making use of that 2. You're multiplying by 2 one more time. When I go to the left one, I'd be halving my distance away. So that's half what it previously was. When I go over, it's half what it previously was. And again, it's distance from the asymptote. I only hope I get to do another problem, assuming that it's in this packet. We'll see. But I have no idea. I didn't look at these problems beforehand, so I don't know which kind I'm doing. So there's the graph. It's going to be going upward with an asymptote at y equals 0, and it crosses through the y-axis, in this case at 4. So it's not A or C, it's not B, so it must, yep, there it is, must be D. So you can take a look at that graph, and you can see, once again, at 1, 8, 2, 16, there are all those points that we just talked about. Okay, so that one was D on 27. And paper confirms it. Evaluate the series, this to S7. Now S7 means the first 7 terms. And this is also a finite geometric series. Now your geometric series equation, your finite geometric series equation, looks like that. So what we're going to do is look at what a sub 1 is. In this case it's 6, you can see it. We have to figure out what r is, so our common ratio, what we're multiplying each time, and you can check that, you know, as your, I could do negative 24 divided by 6. That equals negative 4. That's the same as 96 divided by negative 24. That also equals negative 4. So you can see our common ratio here is negative 4, and n is 7, because they're asking for that first 7 terms. So let's go ahead and do that. S sub 7 equals 6 times 1 minus negative, whoa, what did that do? Oh, thank you. Let's go back. 1 minus negative 4 to the 7th power all over 1 minus negative 4. The one thing to be careful with, I've seen this a few times, people doing 1 minus negative 4 here and then adding that, and then doing it to the 7th power, or something weird like that, right? Maybe still doing 4 to the 7th power, but you're adding. Be careful. You have to do negative 4 to the 7th power first, then you have to subtract that number. It's order of operations. So I'm sure one of these answers probably has you adding that together and then raising it to the 7th. Be very careful about that. In this case, it's going to be, I don't know what negative 4 to the 7th is, so I'm going to the calculator. Now in this case, I don't know if it will matter because negative 4 to the 7th is a negative number. Sometimes you're not so lucky and it becomes a positive number and you do have to subtract. So this is going to be 1 minus negative 16,384. We're going to divide that by 1 minus the negative 4. In that case, it is 5. So 1 minus that number is 1 plus that number. It's 1 plus the positive version of it. So 6 times 16385 all over 5. Go to the calculator here. I'm getting a number like 19662. 19,662. And that is A. So I'm getting A for number 31. And so is your booklet. I don't even know how many problems we have left. I know that I end on, oh yeah I do. We have 1, 2, 3, 4, 5, 6, 7, 8 more problems. Use the properties of logarithms to evaluate this stuff. Alright, so really all you're asking is what 3 to what power gives you 9, 3 to what power gives you 36, 3 to what power gives you 4. Well, sometimes they're not so easy, right? 3 to what power gives you 36? I don't know, right? I don't know. So it might help to condense this all. Maybe we get a number that really works out for all this. For instance, what if I made this log base 3, I'm not sure, I haven't done this problem yet, of 9 times 36 all divided by 4. Notice how I condensed that? See what I did there? And it looks like this will clean up. I don't want to do 9 times 36 first. I'll do 36 divided by 4. That is 9. So this becomes log base 3 of 9 times 9. Now you could either do this one of two ways. You could either do log base 3 of 81, or you could do log base 3 of 9 plus log base 3 of 9. Notice how we're going to get to the same answer. Log base 3 of 81, that's, if I'm going to work for other properties to help you out a little bit, that's 3 to the 4th power. So that 4 would get multiplied in front and I just totally didn't do that. That 4 would get multiplied in front with log base 3 of 3. Log base 3 of 3 is 1, so this equals 4. Another way is just saying 3 to what power is 81, which is 4. Obviously, as you did that. Log base 3 of 9 is 2. Log base 3 of 9 is 2. And we get 4. So, same answer. A lot of different ways to go about it. Logs, you could just use any property of your liking, as long as it's a correct one and it helps you solve the problem. You could have done it in the calculator, and if you did, you would have done log of 9 over log of 3 if you truly didn't know what it was. Plus log of 36 over log of 3. I don't think this really is the way they're asking you to do it. Minus log of 4 over log of 3. Because, as I said, that is one of the truths. You would still get 4. Strange enough as some of these decimals will appear, you'll still get 4. Number 34. Solve this bad boy right here. Okay. The way that I did that other problem was about, like, notice how I changed 81 to 3 to the 4th power. I'm going to be doing the same thing here. I want to find the same base on both sides. That way, when they're equal to each other, then I could just make the exponents equal to each other. If you know what I was talking about earlier when I did the fraction problem. So here I do have a fraction. That's 1 over 16. So two different bases I can use here that 16 and 64 both work with. 2. I could have done that, where I get 2 to the negative 4th equals 2 to the, these get multiplied, 24x, so 24. And then I set negative 4 equal to 24x minus 18. I could keep going there and solve for x. Or I could have done it with 4. Same idea. 4 cubed, the 4x minus 3. Notice, you'll end up getting the same answer. This is just another multiple of 2 mas than the other one. 3 times 4 is 12. 3 times negative 3 is negative 9. So you'll get negative 2 equals 12x minus 9. Obviously, you can see these are like the same equation, just this is twice as much. So you'd still solve for x. So basically, you're working for the same base. Now, how am I getting from this step to that step? The logic part in your head is saying if you have the same base and you're raising to these powers, if these things are equal to each other, these must be equal to each other. How else can you raise 2 to something and 2 to something and make them equal without these two things being the same? That's the logic part kicking in. And same with the force. The mathematical part that it's good to know is if you take the log base 2 of both sides, then that's where you get the exponent to kick out in front, and like negative 4 times log base 2 of 2, and that becomes negative 4 times 1, which is negative 4. You'll get 24x minus 18, kicked out to the front, log base 2 of 2 is 1, 24x minus 18 times 1 is 24x minus 18, and then you get the numbers that way. So this is really what's going on with it, and that's important to know, especially if you have to take the inverse on your final. I don't remember if you do. If you have to take the inverse on your final, it's important to know. I'll solve the smaller numbered problem. So I'll get 12x equals positive 7, I do believe. And divide by 12, you get x equals 7 over 12. And that looks like it's C, as I'm looking above here. Yeah, so your final answer for this one is C. And another way, obviously, is guess and check. You can try all these things. But if this is part of the free response, you do kind of need to know how to do them. 34, C. Yep. Okay, 35, find an inverse. Well, here you go. But this one's with squares. Find the inverse of this. The inverse is swapping all your x and y values, including in your equation. Anything that was an x becomes a y. Anything that was a y becomes an x. And if you want to write it as the inverse function, you will have to solve for y again. So to do that, I'm going to get y all by itself. So I'm going to add 3 to both sides. So I get 7y squared equals x plus 3. I'll divide both sides by 7. So I get y squared equals x plus 3 divided by 7. And I take the square root of both sides, and I'm going to get y equals the square root, plus or minus the square root, of x plus 3 all over 7. Now, it's not guaranteed that something's plus or minus, but the other idea about inverse, once again, when I graph this, is this first graph right here, 7x squared minus 3, it probably does something like that. Whatever. It's a sharp graph, crosses at negative 3, yada yada. If you reflect across the line y equals x, notice how this other line, well, that's not beautiful, but notice how the other line, even though, you know, maybe you don't see off the top of your head what this one looks like, maybe I don't either, but you know it has to look like this if you're reflecting across y equals x, but it must be a full parabola, that's the point. So the only way for it to be a full parabola is if you do the plus version of this graph and you do the minus version of this graph. Otherwise, it wouldn't. Excuse me. Otherwise, it would be a half parabola, which might look something like, well, these don't have that answer. But A would be your answer in this case. Okay, number 37, if a dart hits the target at random, what is the probability that it'll land in the shaded region? So hitting the target at random means you're equally as likely of hitting a bullseye as you are hitting the outer rim, which is probably true. We're not saying there's any skill involved. The only other thing is really just talking about the fact that you're not going to miss the dartboard. Either you hit it, I mean, you do hit it, so either you hit the shaded or you don't. So probability of hitting the shaded region is the radius, I guess, of this guy is 3 inches, as they're saying. That's 3. So the area of that guy is pi r squared, which is 9 pi. Now that's our desired outcome. We desire to get a probability of 9 pi. And not that we want that. I guess we do, because sometimes closer ones are better points. But desired meaning that's what they're asking us to look for. And we're going to divide it by total area here. So the probability it lands in the shaded region is this divided by total. And the total area of everything is the bigger circle. Now, I'm hoping they're saying that the 12 represents this entire thing right here and not just this little guy right here. So we'd have to do 12 plus 3, which is 15. But because the 12 is kind of written in the middle and they don't specify otherwise, I'm going to guess this whole thing's 12. So the area of the entire region, is pi times 12 squared, is 144 pi. Now, these would be square inches and square inches, but when you divide square inches by square inches, they cancel out, just like the pi's do. Pi divided by pi is 1. Inches squared over inches squared is 1. You'll get 9 over 144, which is, I guess that reduces to 1 over 16, after I've done a lot of conic sections problems. Yeah. So that's 1 over 16. And there's your answer. That probability that it's about 6.25%. Well, it's exactly 6.25%. Yeah, 6% chance you're going to hit in that region. Now, again, this is not drawn to scale, so although you're like, I have a better chance than that, yeah, but this isn't drawn to scale. This should be a little bit bigger of a circle. Maybe a little more like, that's 3, maybe 6, 9, 12. There, that looks a little like 6% out of whatever. Maybe it should be even a little bigger. I have no idea. Okay, number 38. Find f of g of negative 5. Remember, this is f of g of negative 5. So I'll do this two different ways. First way I'll do it is by first finding g of negative 5. And then I'll take the f of whatever this value is. That's negative 4 times negative 5 plus 3, which is 20 plus 3, which is 23. So now I'm going to take the f of 23. F of 23 is negative 2 times 23 minus 7, which is negative 46 minus 7, which is negative 53. So your answer is going to be B. Now that's one way of doing this problem. Another way of doing this problem, all depending on whether it'd be easier or harder, most of the time that's the way you're going to want to do it. But another way of doing this problem is if you want to take the f of g of x first. Like straight up. Like where you plug in g of x, you're going to be taking the f of negative 4x plus 3. So you're going to substitute negative 4x plus 3 anywhere you see x in this equation, which is just right there. Negative 2 times negative 4x plus 3 minus 7. So that's 8x minus 6 minus 7. 8x minus 13. So now, what I substitute negative, what was it? Negative 5 into this equation. Technically it's f of g of negative 5. When I substitute negative 5 into this equation, though, I'm going to get 8 times negative 5 minus 13, which is negative 40 minus 13, which is negative 53. So that may or may not have been more, looks like it was more steps, but either way, you still arrive at negative 53, B, and according to my sheet, yep, B is the correct answer. Okay, we've got 3 more problems, 40, 41, and 42, and I think they're all log problems. Simplify, natural log of e cubed. Okay, you might not know the property that the natural log of e is 1. If you didn't, I do want you to know that the natural log of x is the same thing as log base e of x. So natural log is taking the log with a base of e, which is literally what it means. So you could change natural log to log base e if it helps you. This becomes a log base e of e cubed. And if you know, you can take that 3, multiply it in front with log base e of e. And as you can see, log base e of e, natural log, is 1, as we just said. So this will be 3 times 1, which is 3. So once again, you can do the same thing with natural logs. It's so common. It happens so often. Just like, just like regular log. Like that's why they do base 10. Base 10 is so common that they make sure that it's just implied at that point. Excuse me. And they don't very often do a lot of bases more than 10 with logs. It just doesn't occur that much. That's why, you don't want to write a double-digit log if you don't have to. Okay, 41. Solve log of 3x plus log of 9 equals 0. Round to the nearest hundredth if necessary. I'm going to go ahead and start it away. This is those 10 bases as I was talking about. You can do this one of 2 ways. I talked about those 2 ways that first time I did it. Let me first rewrite this. Log base 10 of 3x, remember I like to use those parentheses, plus log base 10 of 9 equals 0. So first way, like I did last time, if I do the 10 immediately like this, you have to keep in mind that 10 to a sum of exponents is separating these into 2 different exponents and multiplying together, times 10 to the log base 10 of 9, like that. 10 to the 0 power is 1. But on this side, now you can separate, or now you can take these logs away. This becomes 3x times 9 equals 1. If I do that the other way, that maybe, once again, most people do it, which I don't necessarily see why you do one way or the other. They're both kind of the same. The sum of the 2 logs is taking those 2 logs into 1 and then making that a product immediately. 3x times 9 equals 1. And you raise that 10 to both sides, or 0, I'm sorry, 0. And you do that 10 right here, and then, once again, that goes away. You get 3x times 9, which is 27x. We'll do that next step, equals 10 to the 0 power, which is 1. So we're on that step. Either way, 3x times 9 is 27, so 27x equals 1. Divide both sides by 27, you get x equals 1 over 27. Shoot, that's a good one right there, Lightning McQueen. Now, looks like it's not 27, it's not 3. Looks like it's either A or B. I hope you know that 1 over 27 isn't 0.33. You get 1 out of 27 on a test, you can get 33%. Probably a lot closer to that one. That better be the right answer. I can just circle that, write that, and check my answer key. 41, it is B. Okay, your last problem of your final review. Write this in exponential form. There is a transition to get straight from one to the other. Literally what this is, when you solve for a log, this is base, log base 32, so you know that'll be your base. So you, automatically, I think this has to be your answer, because 32 is your base. But log of something gives you the exponent. This answer is the exponent, so there it is. 32 to the 3/5 equals 8. If you didn't know that, that other log property is, as we've been doing, raise these with 32s, just like that. 32 to the log base 32 of 8 is just 8. And as you can see over here, you have 32 to the 3/5. You can probably do more with this problem. You can. 5th root of 32 is 2. 2 cubed is 8. Obviously, this must be a true statement for this to work out. But yeah, that's really all you got to do with that problem. I would recommend you going about it this way, though. I definitely would. I wouldn't want you to try and memorize, where does the 32 go? Where does this and that go? Excuse me, but if you had a problem... Oh, gosh, man. But if you have a problem like this in your multiple choice and you figure out the right answer, and then you have a free response question like that as well, I mean, shoot, go to that. Go back to your multiple choice problem and look at how the transformation worked. That's it's not cheating. It's using your work as you have it. So that was the last one. I'm wishing you best of luck here. because we only see each other one more time. And that will be your final. It is, once again, it's 50 multiple choice questions and 7 free response that might have some extra, A, B, whatever else, or a lot of information to ask of you. All right, so good luck. Here I am, guys. So, I wanted to just have just this last. Oh, take this off, dude. All right, so yeah, that's how I talk in my videos. That's how you guys know how I do it. I want to. I don't know what I want to do, man. I just wanted to sign off and have a big thank you for y'all. You guys really made my year. um, this isn't something that's supposed to be super sad, but it's just something that I just want you guys to really go through your next years in math and feel like that something that we did in here was of impeccable importance in your lives, even if it's why do we got to learn this. Maybe it's more of how does my brain now work in different ways, and I just hope that you had fun with that. I really do. But no, definitely, I couldn't have really had a better group of people. Just starting from the very beginning of the year, just thinking about. I mean, if you guys, you guys do know the story. My dad passed away the day before school started. So for me to have that, for me to have my concussion, and which I still have, these distractions in my life, which are you guys, that make every sixth and seventh period fun, that I look forward to when those bells ring, and that I unfortunately have dismay of when the final bell rings and you guys leave, and I just wish I could be with you all the time because I have softball after school and all that other stuff. So all that time is super valuable to me, and obviously, I wouldn't be a teacher if it wasn't. I mean, I really wouldn't be a teacher if it wasn't, because what other kind of value do you get, if you know what I mean? But so anyway, I have ultimate faith in you and being able to do any of these kinds of problems. Absolutely. And I'm more than happy to do these videos for you guys. Obviously, otherwise, I wouldn't be doing them. Enjoy this weekend. Enjoy Memorial Day weekend. If you have any questions, you kind of have to reserve them. But I'm sure you guys will do fine. I have firm belief that I prepped you guys to the point that you guys know what you're supposed to do. I do. I have confidence in myself that you have confidence in yourself, really. And you know what? You guys can do it. You guys can do it. So I will see you guys on Thursday. Good luck. And this was a fantastic year. Okay. I'm not going to cry. Signing off. See ya.